Clinical treatments for diabetes typically prioritize managing blood glucose levels, but the elevation of blood sugar is a downstream effect of a mechanical failure inside the cell. By the time hyperglycemia presents on a standard blood test, a systemic signaling cascade has already broken down. At the center of this cascade is insulin. This hormone operates as the master anabolic switch, coordinating energy storage across muscle, liver, and adipose tissue. When you consume food, insulin triggers a shift from breaking down nutrients to actively storing them. Insulin executes this shift by targeting three sites: the liver, skeletal muscle, and white adipose tissue. To understand how insulin resistance develops, we have to map the exact molecular logic of the signaling cascade within these specific tissues. The process begins at the cellular boundary with the insulin receptor tyrosine kinase, or IRTK, a transmembrane protein residing on the surface of target cells. Insulin molecules bind directly to the extracellular domain of the IRTK. This binding event forces an immediate conformational change in the receptor, causing its internal tyrosine residues to autophosphorylate. This schematic details the reaction. The phosphorylation recruits insulin receptor substrates, which in turn activate the PI3K enzyme. PI3K then catalyzes the production of PIP3. The newly generated PIP3 molecules act as a beacon, recruiting and activating protein kinase B, commonly referred to as AKT. AKT is the central junction of insulin's metabolic control network. From this single node, the initial insulin signal branches out to execute diverse, organ-specific effects. This diagram illustrates the specific intracellular mechanisms of insulin. Looking at Section A, we see the muscle-specific pathway, where AKT activation directly drives systemic glucose disposal. AKT moves to inactivate AS160. This is the protein responsible for keeping glucose transporters sequestered deep inside the muscle cell. Simultaneously, the activation of the RAC1 protein switch causes the cell's cortical actin to reorganize, clearing the physical path for the transporters. With the path clear, GLUT4 storage vesicles physically translocate to the plasma membrane, fusing with it to pull glucose out of the blood. AKT also phosphorylates GSK-3. This specific branch of the cascade initiates the net synthesis of glycogen, storing the newly acquired glucose as muscle fuel. Removing FOXO1 from the nucleus represses the expression of key gluconeogenic genes, specifically G6PC and PEPCK. This mechanism serves as a molecular off switch, effectively halting the liver's internal glucose production during the fed state. While shutting down glucose production, AKT simultaneously upregulates SREBP1C, the master transcriptional regulator of fat synthesis. Insulin exerts control over the liver through this dual mechanism, shutting down the production of new glucose while actively driving the manufacture of lipids. Over in white adipose tissue, insulin activation triggers the PDE3B enzyme, which strictly inhibits lipolysis, the breakdown of stored fats. By keeping these fats locked in the adipocyte, insulin reduces the availability of the raw substrates the liver normally uses to synthesize glucose. However, if the system is chronically overloaded, lipids accumulate outside of adipose tissue. This ectopic lipid accumulation within the liver and skeletal muscle cells is the primary mechanical driver of insulin resistance. These excess lipid molecules act as a physical barrier. They interfere with the connection between the insulin receptor substrate and PI3K, severing the signaling cascade entirely. With the molecular pathway physically blocked, the systemic signal dampens. The target tissues no longer respond to normal physiological levels of insulin. In response, the pancreas attempts to force the blocked pathway open. The beta cells pump out massive quantities of insulin to overcome the cellular resistance. Chronic hyperinsulinemia places immense stress on the pancreas. Eventually, the overworked beta cells fail, marking the transition to clinical type 2 diabetes. Once the endogenous beta cells fail, the patient loses their biological, real-time molecular feedback loop. Replacing this loop requires manufactured insulin to mimic the complex, continuous basal and bolus rhythms of a healthy human pancreas. This chart maps the pharmacokinetic profiles required to manually manage blood sugar, comparing the concentration curves of rapid-acting through ultra-long-acting synthetic formulas. Manual injection. The focus has shifted toward automated insulin delivery ecosystems that attempt to restore real-time sensing and dosing. The patch pumps process the CGM data, continuously calculating and adjusting insulin delivery without requiring direct patient intervention. The hardware itself has evolved into tubeless, highly interoperable systems designed to maintain discrete, 24-hour glucose stability. These closed-loop systems are the ultimate engineering attempt to compensate for the severed biological signal, artificially replicating the precise molecular timing of the PI3K-AKT pathway.